Training a large model is a battle against two enemies at once: memory and time. Every number the network stores and multiplies eats into your GPU, and every operation costs you wall clock hours. So here's a tempting idea. What if you did most of the math in a smaller, faster number format, and only fell back to the precise one where it truly matters? That trade-off has a name: mixed precision training, and it's now standard practice for nearly every large model. Let's unpack how it stays safe. The whole idea lives in a single comparison, so let's put the two approaches side by side. Over on the left, run everything in full precision, using 32-bit floating point for every value. It's rock solid and never runs out of range, but it doubles your memory footprint and leaves modern tensor cores idling. Safe, yet slow and heavy. Over on the right, move the bulk of the work down to 16-bit, cutting memory in half and roughly doubling throughput on the right hardware. The catch is range. The smaller format represents fewer values, so tiny gradients can slip below what it can hold and vanish straight to zero. So we keep a small safety net in the wider format, and that's the trick that makes the whole thing viable. Let's follow a single training step through the loop and see exactly where each format does its job. Begin with the forward and backward pass, run mostly in the smaller format. This is where the speed and memory savings come from, because the heavy matrix multiplications land on the fast tensor cores that are purpose-built to chew through 16-bit numbers quickly. Before backprop, multiply the loss up by scaling factor. This shifts those tiny gradients upward into the representable range of the small format, so they survive instead of underflowing quietly to zero. That single trick is loss scaling. Meanwhile, keep a master copy of the weights in the wider 32-bit format. The optimizer applies its updates to this precise copy, so even the smallest weight changes accumulate correctly over thousands of steps and never get rounded away into nothing. Finally, divide the gradients back down to undo the earlier scaling before the update lands. The precise master weights step forward, then get cast back down for the next fast pass, and the whole loop repeats. Now, boil this technique down, and 3 pieces of doing all the real work. Low precision math for speed and memory. Running the forward and backward passes in the smaller format has memory and unlocks the fast tensor cores built into modern GPUs, which is exactly where that roughly doubled throughput comes from. A precise master copy of the weights. Kept in a wider format, this is the version the optimizer actually updates, so tiny but important weight changes are never lost to rounding along the way. Loss scaling to protect the gradients. Multiply the loss up before backprop and small gradients land inside the representable range. In the newer BF16 format, trading mantissa bits for a wider exponent gives enough range to often skip this step entirely. Alright, let's pin down the 4 things worth remembering. Training this way runs most of the math in a 16-bit format, which has memory and roughly doubles throughput on modern GPUs. The danger is underflow, because tiny gradients can drop below what the small format can represent and disappear to zero. Safety comes from 2 guards, a precise 32-bit master copy of the weights, plus loss scaling that lifts small gradients into range. Eventually, a format called BF16 widened the exponent enough to often drop loss scaling altogether, and today this recipe underpins nearly all large model training. Want more of these techniques untangled clearly? You'll find them waiting at Standarity.com.